Welcome 6th grade students. We are going to take a look at week 18 Bellwork, which again is assigned on Mondays and due on Fridays. I've found that lots of students are asking questions during the week, so I thought we'd resume some videos and see if that might help some of you get your work done while you're at home, so that it's not something that you're worried about while you're at school during math enrichment or reading enrichment and that sort of thing. So if you take a look here, your very first problem says there are 98,515 trees at Washington Park. If there are 17 acres of land and the trees spread out evenly, how many trees are there on each acre of land? So when I think about this, I'm thinking I can kind of picture or visualize, which is a good strategy in math, also in reading, that there are a whole lot of trees, 98,000 and some, and I'm trying to split them into equal acres. It says that they're spread out evenly. So to kind of visualize that, I have a bunch of trees, lovely trees, and I'm going to start splitting them into 17 acres. So I could kind of like start boxing them off. That'd be 2 acres, 4 acres, I could get 8 acres, and I could keep on going with that idea. So when I'm splitting something up, I'm actually thinking about the operation of division. So I kind of want to do a better bar model, but that's just kind of my quick visualization of what was going on there. So if I picture the entire bar representing the total number of acres, there are 17 acres. And the total bar would represent the total trees, 98,515 trees. And if I could, I'd split this into 17 pieces. That would require 16 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That'd be 17 parts. And I'd have to extend my bracket a little bit to show you this. All right, well, in this case, I would go for the total number and I would divide it into parts or into groups. So that's my hint. It says today, take your total, as in the total number of trees, and we are going to divide it into groups, or acres in this case. So let's go ahead and set up our 98,515. That's the total trees, and we're splitting it into 17 parts or 17 equal acres. I will remind you that you're allowed to use a multiplication chart on this, or if you use a calculator, you have to show us your steps. So I would still take it in parts, just number pieces. Something else I will tell you is that with the M step coming up soon, I'm guessing they're not going to let you use a multiplication chart up to 17 or even a calculator on this type of problem. So we might even practice skip counting first by 17s just to see if we kind of have a handle on what we might try to get ourselves started. So 17 times 1, of course, is 17. And if I'm thinking about this, I might think 17 is almost like adding 20, but then taking away 3. So 17 plus 20 makes 37, minus 3 makes 34. I could try that strategy again. Add 20, take away 3. So 20 plus 34 would make 54. Take away 3 would make 51. I could try it again. I could add 20 and take away 3. So adding 20 to this would get me 71. Taking away 3, well, I could take away 1, I'd be at 70. Take away 2 more, I'd be at 68. And I'm going to keep doing this strategy for a little while here. 68 plus 20 would make 88. Minus 3 would make 85. And I could try it again. 85 plus 20, ooh, that gets me up to 105. Taking away 3, I'd be at 102. And I'll try one more just for fun. 102 plus 20 is 122. Take away 3, let's see, 122, take away 2 would be 120. Take away 1 more, should be 119. I also am going to kind of watch to see if I see any numbers repeating at the back. 7, 4, 1, 8, 5, 2, 9. Not really a whole lot yet. So sometimes that will help me if I am kind of looking for patterning. You might notice that something's happening with that last digit, and it will help you check to see if you're doing the multiples correctly, kind of in your head or off to the side. You could also try them out. All right, let's use what we have and see what we can do. So the first thing I'm going to start with is just treating this 9 in the 10,000s place as 9 groups of 10,000. If I have 9 groups of 10,000, can I give you 17 groups of them? The answer would be no. I'd put a 0 up top. Well, some of you like to do 0 times 17 and record the 17 here. I don't think that's really necessary. I know I'm still going to be left with those 9 groups of 10,000. So let me trade that in a little bit or switch it up a little bit, and I'm going to think about this as 98 groups of 1,000. So 98 groups of 1,000. Could I give you 17 of them? Sure I could. Could I do it repeatedly? Absolutely. In fact, you want to get as close as you can. So I notice over here, 85 is pretty darn close, isn't it? In a minute, we're going to take away 85 from the 98 thousands that we have. We're going to use up 85 of those thousands. but I need to think about what multiple that was. So down below here, I could kind of count off times 1, times 2, times 3, times 4, times 5. That's my fifth multiple, isn't it? So a 5 goes up top, meaning I could create 5 groups, or I could put 5 of those trees in each of those 17 acres, if you will. It actually ends up being 5,000 trees, by the way. All right, when I subtract here, 8 take away 5 gets me 3 leftover thousands. 9 take away 8 in the 10,000 place leaves me with 1 10,000. All right. Well, if I have 13 thousands, I can't give you 17 of them very easily unless I start splitting them up. So the next thing we would do is we think about bringing down the next place value. If I have 135, I'm wondering if 17 goes in there. Well, I'm guessing it does, but I kind of stopped my skip counting here, so I might have to pick that up again. After 119, I'd add 20. I would be at 139. Take away 3, I should be at 136. I'll try it again. I'll add 20 to 136. That'd be 156. Take away 3 should be 153. And I went a little too high, didn't I? So I can stop back here at the 136, I believe. So let's go ahead and see what multiple that is. First, second, third, fourth, fifth, sixth, seventh. That's the 8th multiple. So I'm going to put an 8 up top, meaning I can put 800 of those trees in each of those acres. So 8 times 17 got me the 136. Oh, and I just goofed again, didn't I? Actually, 136 is a little too high. So I need to back up a second. Just notice that. And I don't think I can make 136 of them. I can't use up 136 if I only have 135 of those trees to work with, and actually it's 13,500 trees to work with. But regardless, I will go back to this next multiple, or the previous multiple of 119. That will be better for subtraction. And I also need to think about what multiple that was. Well, I think that was the 7th multiple, but we'll double check. Times 1, 2, 3, 4, 5, 6, 7. It's definitely the 7th multiple. I can put a 7 in my quotient. Well, 7 times 17 did get me 119. I will subtract here. There is a little regroup involved. So most of you would go to the 3 and make it a 2, or leave him with 2, and change this 5 to 15. Well, 15 take away 9 gets me 6. 2 take away 1 gets me 1, and 1 take away 1 gets me 0. All right, I'm really ready for the next step, it looks like. So I bring down the next place value, and here I have a 1. So I could treat this like 161. Technically, if I want to go back to the beginning, there's a comma in here, so it's the same as starting with 1,610 trees, but we don't always think about those steps, do we? So how many 17s go into 161? Oh, I'm darn close right here, aren't I? 153 looks pretty close. But what if I added another 20 and took away 3? Well, 20 plus that is 173. Take away 3 would be 170. That's a little too high, isn't it? Let's go back here. This is the 9th multiple, isn't it? So I'm going to put a 9 in my quotient. And 9 times 17 should get me 153 according to my math earlier. All right. Next, I'm going to do a little regroup again, because 1 take away 3 would usually get me a negative number. And to avoid that, I'm going to go to the neighbor and leave him with 5 and regroup to make this 1 a 10 plus 1, or 11. 11 take away 3 leaves me with 8, and I might be counting backwards. 11 in my head, count backwards. 10, 9, 8, that works. 5 take away 5 leaves me with nothing, and 1 take away 1 leaves me with nothing out there in the thousands place. I have one more digit to bring down. It happens to be in the ones place. I now have 85 trees that I'm trying to place on 17 acres nicely, or evenly, or equally it says, I think, of the problem. Evenly it says. And so that means I'm trying to figure out how many times 17 goes into 85, or how I can break those 85 trees into 17 acres. Well, I see 85 on my list again. Perfect. And if you remember, that was our 5th multiple. I'm a little bummed that that 9 should be a little better above my 1, and the 5 should be right above this 5 that I'm using now. And 5 times 17 gets me 85, and when I subtract, there's nothing remaining. We actually have a whole number of trees that we could place on each of those acres, or approximate on each of those acres. So how would we rewrite this? Probably 5,795. And we want to make sure we're answering the question where it says how many trees. That's what they're asking. I would call this trees. We can box that in or frame it. It seems to be our answer. So kind of a couple steps involved here. Maybe a bar model helped us to see that we needed to divide. Next we did some long division, and we talked about skip counting by 17 to try to help ourselves out with a strategy today. Let's go ahead and move to the next problem here, where it says find the sum. And there is a hint here, but I hope you remember whenever we're adding or subtracting decimals, the rule would be you have to line up your decimals. So I hope that's something that you would have thought of without my little hints on the board, but we will give it a try regardless. Now, I noticed a little bit of a problem just peeking at these numbers. Now, this number has a lot of digits, this one has fewer. I also noticed that the decimal here has 1 digit behind it, but the decimal here has 2. So if I want to line up my decimals, I really would like to see 2 numbers, 2 digits behind each of those decimals. Well, that kind of gives me a hint that I might want something behind that 2. And what would be okay to put in there that would not change our value, but just might help us with our lineup? Maybe you're thinking about a placeholder. That's what I was thinking about. All right, lots of students struggle with this idea of lining up decimals, especially when the numbers are so big. So my thought is draw your decimals first. In front of the first number, how many decimal places do you, how many place values do we see? 1, 2, 3, 4, 5. So I'm thinking I need 5 numbers up front. 1, 2, 3, 4, 5. And how many digits did we say we wanted behind the decimal? 2. And I'll kind of start filling them in now. So those 5 digits out front should be a 1, and a 3, and a 1, and a 3, and a 1. And that 2 lands behind the decimal, and I still need to think about what might go there in a minute. Well, underneath here, I lined up my decimals first thing, and I noticed that there are 3 digits in front of my decimal, so I'm thinking about 3 place values here. So I'm going to start with the 1 and the 3 and the 8 all lined up nicely. My decimals are still in alignment, and right behind here I noticed that I have 2 digits, a 1 and a 3. I really want to work on adding these together, but I noticed that there's nothing sitting here. So one way of recording that place value, or keeping something there so that we can work with it, might be to put a 0. This is the same as 2 tenths at the back, or 20 hundredths, I should say. All right, let's go ahead and do some addition. I start here in the smallest place value at the right, so I have 0 hundredths plus 3 hundredths leaves me with 3 hundredths. Next I move to the tenths place, and I'm adding up in these columns. I have 2 tenths plus 1 tenth leaves me with 3 tenths. Notice our lineup is happening here with the decimals. That's a big indicator that those decimals are going to come straight down. They're keeping my place values alike or in common. Next I move to the ones place. I have 1 1 plus 8 ones leaves me with 9 ones. Again, I'm staying in these columns the best I can for you today. Now I move to the tens place. So in front of the ones we have the tens, 3 tens plus 3 tens, or 30 plus 30 gets me 60, or 6 tens. I'll record the 6 here in the tens place. We'll move out here to the hundreds place. 100 plus 100 leaves me 200, or a 2 in the hundreds place. Next I'm moving over here to the next place value. You remember what this one's called? In front of the hundreds? That comma might have helped us read it, huh? This is the thousands place. So I have 3 thousandths plus, ooh, nothing here. Maybe a placeholder would be a good idea, and you'll notice that you're still left with 3 thousandths. If I do that again in the 10 thousandths place, I have 1 group of 10,000 plus nothing here, so maybe a 0 would help me maintain that place value. And I could say 1 group of 10,000 plus no groups of 10,000 leaves me 1 group of 10,000. I really have a final answer. It might be a good idea to put some notation in here to help us read it. So do you notice that in front of the decimal I have 1, 2, 3, 4, 5 digits? If you remember, we reserve the ones, tens, hundreds place. We put a comma, and that helps us read the thousands and 10,000s in a second. A final answer here would be 13,269 and, we say and when we get to that decimal, 33 hundredths. That lands in the hundreds place, doesn't it? Really huge number. So kind of a refresher, when I'm adding and subtracting decimals, it's critical that we line up our decimals. Also notice that I use these lines to indicate how many digits before and after the decimal. That kind of helps me make sure things stay in alignment. Let's move to the third problem tonight, or today, depending on when you're seeing this. And this problem says find the quotient. And I feel like your core teacher might tell you, oh, these numbers are too huge, maybe just skip it. Actually, on your first problem up there, I changed the number from whatever I think it was originally there to 17. I thought it'd be a little bit nicer to work with for us. But this one I kept the same. I thought, okay, we'll handle something bigger. It goes off the charts. We're counting by 42s. So if this shows me find the quotient, I recognize I'm finding the answer to a division problem. I also noticed that we should probably count by 42s because my chart doesn't go that high. So I give you a hint here. I would think about this as adding 40 and adding 2 more each time. So 42 times 1 is, of course, itself, 42. But what if I added 40 to that? 42 plus 42, maybe you notice that that's the same as 82 plus 2 more, 84. Now I have 84 plus 40, that would get me 124, plus 2 more should get me 126. And I could kind of continue this pattern counting by 42s. So 126 plus 42, kind of lined it up here if I need to see it. Oh, yep, I can see that that tens place is going to change. I'm going to have 168 when I'm done. 106, oops, easy for me to say. 168. Let's try that again. I'm going to add 42 to this. So when I add 40 plus 160, I get 200, plus 2 more. Added to that 8, I get 210. And I feel like I don't like the way I did that one mental math style, so I'm just going to double check it. Nope, 8 and 2 is 10, regroup. 6 and 4 is 10 plus 1 more makes 11. Yep, things are good. All right, 210 plus 42. Maybe you can see that the 42 would be lined up here, and you're thinking to yourself, oh, the tens place is going to change by 4 groups of 10, and the ones place is going to change by just 2 more. I should get 252. We're going to try it again. I'm adding 40 and then 2 again. So 40 changes a tens digit. So I have 292 plus 2 more should make 294. I'm going to try this again. I'm going to add 42 to this number. It is a little bit trickier to see this one maybe because there's a regroup involved, so do be careful with that. My mental math students sometimes struggle with that regroup more than anything. So I have 9 tens plus 4 tens makes 13 tens. I'm going to have a little regroup up here, aren't I? So I'm going to end up with 336 when I'm ready, 336. And if I add 40 to this, I have 376 plus 2 more would make 378. And we'll try one more for fun and hope we went far enough. If I add 40 to this number, it's going to change a tens digit, okay, and also a regroup I see. So I'm going to have 418 plus 2 more, 1920, 420. And I'm going to stop there for a quick minute. That makes good sense to me. This is probably the 10th multiple, and when I multiply 42 times 10, I should get that 0 at the back, right? This is making good sense. Let's go ahead and set up our long division now. So trying to teach you some other strategies as we move along. I'm going to use 42 as my divisor, and 26,000, that first number, dives in. It's also known as the dividend. Students hate when I say that, but I actually think it's a really good strategy to remember, or tool to remember. All right. We're going to start out here in the largest place value, being the 10,000s place. If I have 2 groups of 10,000, can I give you 42 of them? Not very easily, so I'm going to put a 0 up top and say I did try. Next, I have 26 groups of 1,000. So if I have 26, am I able to give you 42 of them? Not very easily, so I'm going to put a 0 up top and say let's try the next place value. What if I treated this instead like 262 hundreds? So this is in the hundreds place. If I have 262 of something, could I give you 42? Sure could. Could I get even closer than that? I could use up 252 of them, couldn't I? So that's what we're going to do, using up 252 of those 262 that we had available. And I need to figure out what goes into my quotient. So how many times did 42 go in there? Let's go ahead and count off our multiples. This would be the first, second, third, fourth, fifth, sixth multiple. So a 6 goes in our quotient. 6 times 42 should get me 252. And in fact, if I check it, mental math, 240 plus 12, it works. Let's go ahead and subtract. 2 take away 2 leaves me with 0. 6 take away 5 leaves me with 1. And 2 take away 2 out here leaves me with 0. This is great. I can check. I know this 10 is smaller than my divisor. Things are going well. I'm going to bring down the next place value and try again. If I have 100, am I able to give you 42 of them? Well, sure I can. Can I give you more than 42? Could I give you 42 a couple times? Let's get as close to 100 as we can with our division. So if you look over here, 84 is darn close, isn't it? So I'm actually going to use up 84 of those 100 pieces. But I need to figure out what multiple that was. So first multiple, second multiple, that means 2 groups of 42. Got me the 84. Let's go ahead and subtract here. There is a little bit of a regroup. Another way to think of this might be to say this. If I had 100 take away 80, 100 take away 80, maybe you're thinking about being left with 20, right? But you need to take away 4 more. So 20, counting back 4. So I'm thinking 19, 18, 17, 16. I'm using my touch points here. I'd be left with 16. And of course, you can regroup a couple times there. That would also work. 16 is smaller than 42. I know my divisor is larger than what I have for leftovers, so things are going well. I used up as many groups as possible, and now I bring down this 8 and treat this like 168. If I have 168 of something, can I give you 42 of them? Yes. Can I do it again? Sure. How many times could I do that? Looks like I could get right to 168 without going over. I have 1, 2, 3, 4 groups of 42. Gets me 168. And when I subtract, there's nothing remaining. We ended up with another whole number on this one. So 624 is our final answer. This makes pretty good sense to me. If I treated this like 600 with some estimation skills, and I treated this like 40 instead of 42 with some estimation or some rounding, I might say, I know 6 times 4 is 24, and I have 1, 2, 3 extra place values behind it. So 24 with 3 extra place values. Yeah, this is pretty darn close to 24,000, isn't it? Good estimation. All right, let's go ahead and try the last problem on this page. Where it says there is a string of red and blue lights strung around a window. The red lights blink every 3 seconds and the blue lights blink every 5 seconds. I'm thinking I'd get a headache. Next it says, how many times will they blink at the same time in 1 minute? Oops, that should probably not say 1 minute. It should probably say in 1 minute. Helps if you're on a pen also. All right, so we'll fix that up a little bit. So you're helping me be a better editor for next time around. Then there's a hint. It says hint, 1 minute equals 60 seconds. So let's try this again. I'm picturing this red light blinking, this blue light blinking, and they're blinking at different times. Red lights are blinking every 3 seconds. So I was thinking about counting by threes. 3 seconds, 6 seconds, 9 seconds. And then in a minute, I'm going to have to think about blue. So it says the blue lights are blinking less frequently, every 5 seconds, right? So I'm going to count by 5 seconds. 5 seconds, 10 seconds, they're going to blink again, 15 seconds. So let's go ahead and do our skip counting together and see what we notice. Counting by threes, 3 times 1 is 3, 3 times 2 is 6, 9, 12, 15. Hopefully we're getting really good at recognizing these. 18 plus 3, 21, plus 3, 24, plus 3, 27. Let's do one more for fun, 30. Okay, that's not bad. Let's see if we can count by fives next, and I'm going to change to my blue pen just to emphasize these are the blue lights every 5 seconds. So the first time they blink is at 5 seconds. The second time they blink would be at 10 seconds. They'll blink again at 15. And notice I am just skip counting for you. 20, 25, 30, 35, 40, 45, and one more for fun, 50. I should have had a comment in there. All right, so the question is, how many times will they blink at the same time in 1 minute? Well, I don't know exactly where 1 minute is unless I look at this hint and I think to myself, I know in 1 minute I'd find 60 seconds. So instead of stopping here with my red lights at 30 seconds, I might have to keep going till I hit 60 seconds. And instead of stopping here with my blue lights at 50 seconds, I might have to go a little bit farther till I hit 60 seconds. So maybe I'm going to head back for a quick second and see if I can continue those lists. So after 30, I was counting by threes. 33, 36, 39, gonna run out of room here. 42 plus 3, 45 plus 3, 48 plus 3, 51 plus 3, 54, oh we're close, plus 3, 57 plus 3 is actually 60, gets me right to 60. I'm going to go back and count my blue lights off a little bit, so if I can try to change pens for you, tighten with this a little bit. I left off at 50 seconds, right? But here I was counting by 5, so go back and notice the pattern, 5, 0, 5, 0, 5, 0 at the back. So next after 50, I'd have 55, and then I'd have 60. Oh, I didn't have very far to go with those, did I? Now remember, it's asking how many times will they blink at the same time, so I'm going to kind of circle my question. I love to do that and kind of indicate that's what I'm trying to find, the same time. So let's look for some common numbers in our multiples list. So what's the first thing you see they have in common? I notice that they both have a 15. Keep looking. Do you notice anything else that they have in common? No, hopefully you notice that they both have a 30. And anything else you see here? Oh, they both have a 45. And if I keep on going, oh, they both have a 60. And the 60 is hiding back there, isn't it? I don't know how I'm going to circle that for you. It's back there. It sure is. All right. So the question is, how many times will they blink at the same time in 1 minute? I think I just found them all. So instead of thinking about 1 minute, I thought about 60 seconds, and I did my multiples all the way to 60, and I'm going to see how many things they have in common. Well, 15 is 1. 30 is the second common multiple. Here's the third common multiple. Here's the fourth common multiple. It seems like they're going to blink 4 times at the same time. They're going to blink 4 times together. How's that? And while it's exciting to have an answer and go, yay, let's move on, I do have to mention something to you that I hope you're noticing. Do you notice that there's kind of a pattern to the numbers that were in common? I notice it, first of all, with the 5s, actually, because these are closer together, aren't they? It's kind of like skip a multiple, boom, there's a matching multiple. Skip a multiple, bam, there's a common multiple. Skip, skip, bam, skip, skip, bam. That's going to continue as I keep going with my multiples. And that's kind of helpful to make sure that, you know, I'm finding what's in common and I'm being careful about my skip counting or my math. There will be a pattern to that. So what's the pattern counting by 3s? If you notice, it looks like it's every 1, 2, 3, 4, 5th multiple. 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 So there's also some patterning to that that might help someone else find this answer in another way or a little bit more quickly, which I think is kind of fun. All right, moving on to the next problem on the next page. Friendly reminder, don't watch this whole thing if you don't need it. Move to the parts of the word problems or the parts of the review problems that you're looking at for 6th grade math that you need the most help with. And then maybe try it on your own and then go back and just use this as a checking tool more than anything. Or if something went wrong, that's your chance to dig in and figure out, what should I try differently? This next problem says complete the table. I have adults and children. So for one adult, they can handle about 9 children. That sounds about like what I could handle right now, if that. What if I had 2 adults? Well, they could handle more like 18 children. So I'm kind of picturing like chaperones or something on a field trip. If I have 1 teacher, well, they can have a group of 9 students. If I have 2 parents, well, we could handle 18 students into 2 different groups, right? Well, what if I had 5 adults or 5 chaperones on the field trip? So I want you to notice a pattern. Maybe someone says, well, each time, each adult gets 9. So this is kind of like the second multiple of 9 is 18. The third multiple of 9 would be 27, but I want the 5th multiple. So maybe you notice something like that. Here's something else you might say. You notice that to go from 1 to 2 adults, they doubled it. Well, to go from the children, 9 children, to 18, they doubled that. So they're using the same rules. Let's look at this next one. If I have 1 adult, but I want 5 adults to go instead, I'm actually increasing the number by 5. I'm multiplying by 5. And if I do that to the left or to the adults, I do that to the right or to the children. What is 9 times 5? Well, whatever that multiple is will help you find this answer. I'm going to give you a hint on this next one, and I'm going to let you kind of go back to the original rate or comparison. And here I have 1 adult, and I want to change to 6 adults or 6 chaperones. I want to figure out how many children I could take maximum on the field trip, right? If I have 6 adults or 6 chaperones. Well, how did you go from 1 to 6? And you might notice the number is growing. So is that multiplication or division in most situations? Hopefully you say it's multiplication. We're multiplying by what? 6. If I multiply the adults by 6, it also means that I can multiply the children by 6. So whatever 9 times 6 is will determine how many children could attend with 6 chaperones or 6 adults. Notice I did not give you answers here. So I kind of led you there. I gave you kind of a strategy to think about, and hopefully you end up with 2 answers for us. So I could write them when I'm done, right on that table, just make sure that they're obvious, or I could maybe write them off to the side and say for 5 adults, I would get this many children. For 6 adults, we could take this many children. All right, next let's talk about tacos, which is really a dangerous thing because I haven't had dinner yet tonight. So on this next problem, it says a box of 12 tacos cost $9.99. At this rate, how much does 1 taco cost? So I kind of set up that same sort of flow chart that we've been using in math class lately. We kind of used this when we were talking about rates. We're doing something like this now that we're talking about percents. But I want to take the original information and kind of think about, all right, what do 12 tacos cost me? 12 tacos cost $9.99. So 12 tacos, tacos on the left, money on the right, $9.99. But I don't want 12 tacos. They want to know how much just 1 taco costs, or per taco we might even say. So if you remember doing that before, if it says per taco, we're talking about just one of them, we have to break down that rate. We have to make it a little bit smaller, don't we? So instead of having 12, I'm splitting this number up. I'm making it smaller. I'm dividing by 12 itself. And if I do that to the left, I do that to the right. So if I do that to the tacos, I also do that with the money. Now this one I think could be a little bit tricky. I haven't really tried it out, but I'm picturing to myself that maybe 12 doesn't go in here nicely. I don't know if that's true or not. So the first thing I'm going to remind you is put the money in, put the quantity out, and divide it all about. I won't sing for you right now. It's a little too late, and I don't want to give anyone nightmares. But anyway, I'm going to remember this strategy because it always helps me find unit price or unit rate, or the price of 1 ounce, 1 unit of something, 1 taco in this case. So let's put the money in. We're going to use that money and we're going to divide it into 12 equal parts, or 12 equal tacos, to figure out how much just 1 taco costs. There is a decimal involved in this division problem, and because 12 is a whole number, I get to bring this decimal straight up. It won't affect the place values in my dividend. So now if I have $9, can I give you 12 of them? Not very easily. They're not going to be whole dollars, are they? So I'd put a 0 out front and say, well, I sure did try. Next, I would treat this like $9.90. Well, if I have $9.90, can I split that into 12 equal groups somehow? And the answer is yes. So checking your chart or counting by 12, you might notice that you can get 8 groups of 12 to get you to 96. When we subtract, there's 3 remaining. So you used up $9.60. Okay. The next thing we want to try here is to see how many times, oops, we've got to bring in a place value, don't we? See how many times 8, wrong thing. See how many times 12 goes into 39. So I'm treating this 39 like 39 cents. I want to split it into 12 equal groups. So counting by 12 is 12, 24, 36, 48, too big. So back up. I heard us say 36. That was the third multiple. 12 times 3 is 36. And when you subtract, you're left with 3 cents. Well, because this is money and because we're dealing with decimals, I can't really write this as a mixed number. That would be kind of a inefficient and very uncommon way of writing what's left over here. So I hope you're thinking back to what we've done in a recent unit where we're trying to get as close as we can or as accurately as we can. We might put another place value in the thousands place and bring it down to do a division one more time and help us do some rounding. So next I have 30 divided by 12, counting by 12s again, 12, 24, 36, too big. So we'll back up, 12, 24, oh that was the second multiple, wasn't it? I'll put a 2 above the 0 that I just used, and 2 times 12 is 24. When I subtract, there is something left over. I could count up from 24, or I could recognize 4 plus 6 gets me to 30, or gets me to a total 10, I guess, and 6 would be remaining. I could keep on going. This could last for a while, it looks like. Actually, I might terminate on the next one, but this is enough information for me because money, money, money goes to the hundredths place. So I want to think about money, money, money to the hundredths place. Looking here, I have a decimal place. Behind it, I have the tenths and the hundredths. I like to circle that number in the hundredths place and help him do the rounding. Help him pay attention to who's behind him here. So we like to say 5 or more, raise the score. 4 or less, let it rest. Well, this 2 is definitely 4 or less. It's smaller than 5, isn't it? So I need to round down. What I'm saying to you is, this is either closer to 83 cents or bumping up to 84 cents. And when we say round down or let it rest, that means that we're going to approximate. This is where we break out those noodles, right? That approximation symbol. And we would say that this is closer to $0.83. I'm not going to round up on this situation because this last digit in the thousands place is smaller than 5. So this answer here, I could say that this 83 cents, oops, probably not like that though. This $0.83 is about the cost of 1 taco. And they probably would round up to make sure that they're compensating for that extra penny, right? For that extra amount that otherwise wouldn't be figured in. Good. Let's go ahead and move to the third problem on this side. And if you notice, we're dealing with some division. I have a fraction that's being divided. I have a whole number that's being divided by a fraction. I give you a hint off to the side. I tell you, well, let's think about keep, change, flip. Some of you like to call that freeze, change, flip. And I know for state purposes on our test soon, they're going to say multiply by the reciprocal. Some really fancy words that mean, hey, figure out how many times 2/3 goes into 42. I could draw bar models. I could draw 42 of them. I could start splitting them into thirds and grouping them by 2s. That would take me a really long time just because 42 is so large. So we've learned that there is a strategy that works every time. I might want to turn this 42 into a fraction. So we'd write 42 over 1. And I'm going to line up my letters, keep, change, flip here to kind of help you out. This K tells me to keep the first fraction. So I'm going to keep the 42 over 1. The C tells me to change from division to its multiplication, or its inverse operation, I should say, of multiplication. And the F tells me to flip or write the reciprocal of 2/3, which is 3/2. I am really ready to look for some cross simplifying, and I want to discourage you from cross simplifying until you see beep multiplication happening here. So you kind of have to remember to yourself, do not cross simplify when you see division. Do not with division. So do not with division is kind of a big deal. And right here, multiplication, it's okay to do it now. That's because we're really breaking it down into its factors, or common factors of 42 and 2. All right, both numbers could divide by 2. They're both even, so I'll divide 2 by 2 and 42 by 2. Half of 2 is 1, and half of 42 is 21. So 3 and 1, they do have a common factor of 1, but unfortunately that won't change them a whole lot. So I'm just going to multiply straight across next. 21 times 3 gets us, well, 20 times 3 is 60. 1 times 3 is 3 more. I think I'll get 63. And 1 times 1 on the bottom is just 1. Hopefully you recognize this is an improper fraction. And even better than that, some of you have recognized a pattern to these numbers. But I would take the top and divide by the bottom if I was uncertain. Well, any number divided by 1, what ends up happening? Don't we get the number back itself? Oh, that's right. That's equivalent to a whole number of 63. Now this might be hard for us to think about, but if I have 42 candy bars and I start breaking off 2/3 for you and 2/3 for you and 2/3 for you, I'm going to end up with more than 42 groups because you're getting something smaller than one whole candy bar. So 63 is a good final answer. This last one is a decimal division problem, and I say, hey, remember Simon Says. That's what I like to call it. Again, it's just a mnemonic or another mental strategy to help you remember steps. So, hint, Simon Says. I'm going to set this up like I normally would. So I'm going to take the first number to find the quotient. I'm going to place the first number in. And if you remember in our old notes, we always wrote in and out. It's always a pattern, in, then out. So that first number is in. It's my dividend. He dives in. The second number is my divisor with an extra little loop on it. But anyway. All right, I said place Simon Says. Oftentimes in the classroom we call this Schumann Says. And if you notice, it's because this divisor is a decimal, right? And it's tough to divide by a decimal. It's tough to divide a whole number and some decimal pieces by something as small as tenths. So another way of handling this is to turn this number into a whole number. To do that, we would have to move the decimal 1 hop to the right. Simon Says hop once to the right. Well, if you want to win the game of Simon Says, you better do what Simon says. So if Simon says it, you better do it. Look at this decimal and 8 1/10. Simon said hop once to the right, so we repeat that same process with the dividend on the inside. Now some of you know why that happens. Some of you recognize that I actually multiplied both numbers by, 10. When you multiply by 10, it makes that decimal hop one place to the right. If I multiply by 100, we could hop it twice to the right, but this is enough to get this process going. Well, this is beautiful because I end up with a whole number on the outside. I might do a rewrite step so that my divisor just looks like 3. And inside the dividend now has a new value. I'll treat it like 81. All right, that decimal at the back could be useful, I guess, if we have something remaining. So I'll bring this straight up in case we need to see that in our final answer. All right, starting out here in the biggest place value, also known as the tens place. I have 8 tens. Can I give you 3 of them? Sure. Could I do it a couple times? Sure. Could I do it more than that? No, because when I count 3, 6, 9 is too big. I could give you 2 groups of 3. 2 groups of 3 gets me 6. That's how many parts I'm using up. And when I subtract, I'm left with 2. I have 2 tens remaining, but I don't want to forget that I have some ones to work with also. So here I have 21 ones. And my next step would be to say how many times does 3 go into 21? Well, counting by 3s perhaps. 3, 6, 9, 12. You could keep on going. You would notice that it will go in there 7 times perfectly because 7 times 3 is a 6th grader's favorite number, 21. And when you subtract, there's nothing remaining. We end up with a whole number answer after doing this process of long division, and 27 will work. Now, others of you might like this idea of rewriting this as a mixed number, 8 1/10. And we could divide it by 3/10. If you have really good fraction decimal sense, that will work well for you. You could turn this into an improper fraction and then use that same strategy from the last problem where we did a keep, change, flip, or multiply by the reciprocal. I hope you saw something new, maybe in my strategies or in my thinking that you found helpful today. I hope that this helps you to kick things out while you're at home without me here to answer your questions. And again, I wouldn't totally rely on this because I probably won't do it every week. This is just kind of a fast forward week for us. I know we have to be getting ready for a test soon too. So use this just as tools for checking or when you're really truly stuck, and be prepared to take your percent test happening this week.